way in which drugs move through the body, through the body system.
Excellent. So it's still the kinetics, but now as applied to drugs, right? Thank you. So that's very important to think about. As pharmacists, we're scientists, and our applications of all things related to our science are, centered on how drugs are modified in the body, or how the body modifies drugs, right? And also how the patient experiences those modifications that happen in their body as those drugs come to play, right? So it's very, very key to put that in mind. Now, order of reaction, when we talk about order, you talk about magnitude, which is, a kind of measure of the progress of a reaction. So that's basically what we're going to be discussing today. The order of reaction is a number of concentration terms that determine the rate. They determine the speed at which a reaction is going on, right? For example, consider terms maybe drugs A and B, or maybe drug A in solvent B, reacting to form two substrates, right? C and D. The rate at which this occurs, or the speed at which this reaction happens to form the substrates, will be dependent on either the concentrations of these two, the temperatures at the temperature of the environment in which the drugs are. It can depend on a number of things. So our study at this point is to identify how many things, or what are the things that determine the rate at which these drugs are being transformed, and identify how many things are affecting that order of change, right? So you can have zero order reaction where the concentration or the participating elements, do not contribute to how fast or how slow the reaction occurs. You can also have drugs where the concentration of the drug, determines the rate at which the forward reaction occurs. You can also have a condition where two or more drugs are present, and one is determining the rate at which the other one is, being transformed. So you can have zero order, you can have one first order or one order, and you can also have second order, reactions. And you can even have more than that. You can have three or more, higher orders of reaction. Those are very they're also common, even though most of what you find described in the literature are between zero and second order reactions. It's very likely you will not see that much difference, beyond the second order reactions. Now, the rate of the reaction is proportional to the concentration. In this, example, is proportional to the concentration. Please, if you have a question, please just raise your hands. I will be monitoring I'll be monitoring the room so that I can respond if there are questions, okay? So do me the courtesy of just raising your hands so I can see you, right? So the rate of reaction is proportional to the concentration of A to the power of X, right? That's what we have where when we're saying that the overall equation is rate will be this constant K, right, multiplied by the concentration of A, right, and the concentration of B as well to the power of Y. Now, the overall order of reaction is X plus Y, okay? And the reason why this is so is we're here considering that both the concentration of A and B are contributing to how the reaction is moving forward. If all of the rate at which this reaction is moving forward is depending only on the reaction of one of the substituents, of course, we'll be looking at just the rate of concentration of that substrate, of that drug, I mean. Now, the rate constant K is very important in describing rates of reaction and all of our mathematical calculations relating to concentration of drugs in human systems. Now, a rate constant is a proportionality constant that appears in a rate law. For example, K is the rate constant in this rate law here. If you look here, I know that you've done some bit of introduction to further mathematics where you do a bit of integration and differentiation, right? So you will definitely understand this equation that says that the rate of change of the concentration of A over time T will be moderated by this constant K times the initial concentration of drug A that was administered to that system. So rate constants are independent of concentration, but depend on other factors, most notably temperature, right? Or even the solubility of the drug in the system.